Have you ever stopped to wonder how some materials seem almost too perfect for the modern world? Strong yet light, tough yet elegant, resistant to corrosion, heat, and time itself. One such material is titanium, a metal that quietly supports airplanes, saves lives in operating rooms, and even graces luxury watches and jewelry. But titanium doesn't begin its life as a sleek engineered component. Its journey starts deep within the earth, hidden inside rocks, locked away by chemistry and time. Extracting it is neither simple nor cheap, yet humanity continues to pursue it. Why? And how exactly does raw titanium or transform into one of the most valuable metals of our age? Today, we follow titanium's remarkable journey. From buried mineral to modern marvel, titanium is surprisingly abundant. In fact, it is one of the most common elements in Earth's crust. Yet for centuries, it remained largely unused. Unlike gold or copper, titanium doesn't appear in nature as a shiny, workable metal. Instead, it is tightly bonded to oxygen and other elements, forming stubborn chemical compounds that resist easy extraction. Most of the world's titanium comes from two minerals, ilmenite and rutile. These minerals are typically found in coastal sands or ancient geological deposits formed millions of years ago. Countries such as Australia, South Africa, India, and Canada are among the leading producers, supplying the raw materials that feed global titanium production. Mining titanium ore is an industrial-scale operation. Massive excavators remove layers of earth, exposing mineral-rich sands or rock. The ore is then crushed, washed, and processed to separate titanium-bearing minerals from unwanted material. What remains is far from pure metal. It's only the beginning. If titanium is so abundant, why isn't it cheap or easy to produce? The answer lies in chemistry. Titanium has an intense attraction to oxygen. The moment it's exposed to air at high temperatures, it reacts aggressively, forming brittle oxides. This makes traditional metal smelting techniques ineffective. For centuries, this chemical stubbornness kept titanium out of reach. It wasn't until the 20th century, driven by wartime demands and advances in industrial chemistry, that a practical extraction method emerged. The most widely used method for producing titanium metal involves converting solid ore into a liquid chemical compound. This may sound counterintuitive, but it's the key to separating titanium from its impurities. First, the refined ore is mixed with carbon and exposed to chlorine gas inside a sealed reactor. The temperature climbs to around 1,000 degrees Celsius. Under these extreme conditions, titanium reacts with chlorine to form titanium tetrachloride, a volatile liquid. This step is crucial. Many unwanted elements, such as iron, do not react the same way and remain behind as solid waste. The titanium tetrachloride, on the other hand, can be drawn off and purified through repeated distillation until it reaches exceptional chemical purity. At this stage, titanium exists not as a metal, but as a clear, reactive liquid, dangerous to handle, yet essential to the process. The next phase is where titanium finally becomes metal. The purified titanium tetrachloride is introduced into a sealed chamber filled with either molten magnesium or sodium. There, a powerful chemical reaction strips away the chlorine atoms, leaving behind pure titanium. What forms is not a solid block or shiny surface, but something far more unusual: titanium sponge. This porous, brittle mass resembles burnt coral or compressed foam. While it lacks beauty, it represents a major victory. Titanium, at last, in metallic form. The byproducts of this reaction, such as magnesium chloride, are collected and recycled, helping reduce material waste in the production cycle. Titanium sponge cannot be used directly. It still contains tiny impurities and lacks structural integrity. To transform it into something useful, it must be melted under carefully controlled conditions. During this stage, alloying elements may be added. Aluminum, vanadium, molybdenum, and other metals are introduced in precise amounts to tailor titanium's properties for specific applications. The molten metal is then cast into large ingots, solid blocks that form the foundation for all further shaping and processing. Once cooled, titanium ingots are reheated and mechanically worked. This stage is about strength and structure. Using massive presses and rollers, manufacturers forge, roll, or extrude titanium into plates, bars, tubes, and sheets. Each pass refines the metal's grain structure, enhancing its durability and performance. Titanium's strength-to-weight ratio is one of its defining features. It can rival steel in strength, while weighing nearly half as much. This makes it invaluable in industries where every gram matters. Pure titanium is impressive, but alloys unlock its full potential. By adjusting the composition, engineers can produce titanium materials optimized for flexibility, heat resistance, fatigue strength, or corrosion resistance. These tailored alloys are essential in aerospace, automotive, medical, and marine applications. Some alloys are designed to endure extreme heat inside jet engines. Others are crafted for compatibility with the human body, allowing bone to grow naturally around implanted components. This adaptability is what makes titanium not just a metal, but a platform for innovation. Despite its advantages, titanium is notoriously difficult to machine. It doesn't conduct heat well, which means cutting tools can overheat rapidly. It also resists deformation, placing immense stress on machinery. Specialized equipment, slower cutting speeds, and advanced cooling techniques are required. Yet precision machining is essential. Aerospace components must meet microscopic tolerances. Medical implants require flawless surfaces. Luxury goods demand aesthetic perfection. Once shaped, titanium parts may be polished, heat-treated, or coated to enhance performance or appearance. Titanium's real magic lies in its applications. In medicine, it's used for joint replacements, dental implants, and surgical tools because it's biocompatible and non-toxic. The body accepts it, allowing bone to fuse directly with the metal. In aerospace, titanium reduces weight while maintaining structural integrity, improving fuel efficiency and performance. In consumer goods, its sleek appearance and durability make it popular for watches, eyewear, and high-end electronics. Few materials operate so seamlessly across such diverse fields. Titanium production is energy-intensive. Mining disturbs ecosystems, and chemical processing requires careful waste management. However, titanium's long lifespan offsets much of its environmental cost. Components often last decades, and the metal is fully recyclable without losing strength. Researchers are also developing new extraction techniques aimed at reducing energy use and environmental impact. Electrochemical methods show promise, potentially reshaping titanium production in the future. From spacecraft and submarines to artificial hips and wedding rings, titanium proves that the most extraordinary materials often come from the most challenging processes. So next time you encounter something made of titanium, pause for a moment. Beneath its smooth surface lies a story of heat, pressure, patience, and innovation. From the depths of the earth to the edge of tomorrow, titanium truly is a metal for the ages.